Uh, so that's the topic for discussion today, locking and concurrency control in Postgres. Uh, I'll try to cover a few things around the topic. Uh, about me, I work as a senior principal engineer at EDB. Specifically, I work on project called Postgres Distributed or PGD or BDR, known by different names. I'm also a publicity co-chair for SIGMOD 2026. Like Jayan sir yesterday mentioned about it, SIGMOD is happening for the first time in India in early June, the last week of May and first week of June. And I would encourage all of you to consider participating in the event. It's considered to be the mother of all database events in the world. And I am co-organizer of this event. I just picked up this slide from 2013. This was the first meetup that we did in Pune with less than 30 people, and I'm sort of inaugurating that event with the thought behind starting that meetup. And I think all of that stays today relevant as well. So we'll talk about locking. What are the different locking subsystems that Postgres provides, and what are the nuances between these subsystems. We'll talk about the heavyweight locking, which is probably more sort of relevant for a lot of our audience here, though I see a lot of database developers here as well, so maybe it's going to be a mix of things. And then we'll talk about why some of the locking techniques that Postgres sort of provides are important. So what is the fundamental problem that locking tries to solve? And just like any other complex system, which are typically you would have multi-threaded systems or multi-process systems, they both have a problem where either two threads or two processes are trying to access some data, manipulate data, read, write, and you want to make sure that the system provides a consistent picture to the audience, its audience, right? And that's when locking comes into picture. In case of Postgres, for example, there are different areas like shared memory areas or files, disk files, to which we have to make sure that the access is controlled. And then there are a lot of internal data structures, obviously, that Postgres maintains that users don't get to see, but you need to make sure that those are accessed correctly. So what locking provides? It provides fundamentally four things: mutual exclusion, like where there are multiple processes or threads trying to access data. You need to make sure that, depending on the requirement, right, either the access to that code section is either mutually exclusive, or if they are like only reading, then maybe they can do it in parallel, but another writer should wait for the readers to be done. Data integrity, you have to make sure that data stays, the data integrity is maintained as the system is processing various read and write requests. Consistency is maintained, isolation is guaranteed. Like a lot of these are typical transactional properties that any database system strives to provide, and locking plays an important part in ensuring those guarantees. Obviously, locking is not the only thing, but for this talk purpose, obviously we are focusing on locking. So what problems locking really solve? So let's look at few examples. Like so this is an example of lost updates. So let's say there are two transactions or two sessions trying to make a change to the database, and both of them say select from the accounts table and figure out what's the current balance in the account, and they are trying to say subtract some amount from the account. Now if you don't have locking or some other way of ensuring that the sessions can run parallelly without causing undue sort of effect, if you don't have something like that in place, in this example, for example, like one update is lost because both transactions read the current state of database and they did their own individual things without taking into consideration that there is another transaction that is also working on the same row at the same time. So that's lost update. This is dirty reads, like you have two transactions trying to, so one transaction is making writes, whereas the other transaction is trying to read from the table. And if you don't have proper locking in place, what can happen is the transaction which is reading is, it sees data which is not yet committed. And if, in this case, transaction A or session A rolls back, what sessions B read from database was not actually a consistent state. So, you don't want to have dirty reads in a database. Inconsistent reads, a transaction is modifying multiple things, and then there is another transaction which is trying to read from the database at the same time. You want to make sure that the other transaction either sees everything, every change, or nothing at all. And these kind of inconsistent reads can be prevented via locking. Now, I must say that some of this may not be like exactly relevant for Postgres, because Postgres have the entire concept of multi-version concurrency control, which sort of works together with locking to ensure some of these things. So let's look at the locking subsystems in Postgres. So there are three major subsystems that Postgres provides for locking. The lowest one is, or at the system level, they are called spin locks. Then there are lightweight locks, and then there are heavyweight locks. Now, obviously, in recent years, we use a lot of atomic instructions as well, and you can consider that to be part of like a low-level subsystem as well. But these are the different characteristics of these subsystems. So when you look at spin locks, like the user query would never see a spin lock directly, but at the code level we have to use spin lock quite often, and these locks are meant to be held for a very short duration, like nanoseconds. There are no like read and write mode in spin lock. You take a spin lock, you do something, you release the spin lock. So you are expected to hold spin lock for extremely short duration, like nanoseconds. You are not supposed to sleep, like the process should not sleep while holding a spin lock, otherwise that can lead to like panic in your database. So the developers need to be extremely careful when they are working with spin locks, what they can do and what they cannot do while holding a spin lock. Whereas lightweight locks are slightly more generous. You can acquire a write lock, the LW lock. You can do a disk IO, or maybe even report like a elog message. All of that is okay. There are read and write modes for LW locks, and you can hold them for a slightly longer duration. There are no deadlock detection available for LW locks and spin locks, whereas the heavyweight locks, which are more user-facing locks, they have all of these. I mean, you can hold them for seconds or even minutes or hours or days. I'll talk about some of those things, sometimes intentionally, often unintentionally, but you can do that. There is a fairness queue associated with heavyweight lock. The deadlock detector algorithm sort of works with heavyweight locks. And then there are scopes of LW locks. You can hold heavyweight locks like for the entire transaction duration, or in some cases even beyond a transaction. So I spoke about some of these, like spin locks, like I said, lowest primitive, that sort of the entire Postgres subsystem builds on top of spin locks. Even LW locks are implemented using spin locks, and heavyweight locks are also like at some level would end up acquiring a spin lock. Spin locks are like busy wait. So if you acquire a spin lock, and if there is another process which is trying to acquire the same spin lock, the other process would like consume CPU as it is waiting for you to release the spin lock. So that's why it's very important, even in a multi-process architecture, that you should release spin locks as soon as possible. There is no fairness guarantee. They are held for extremely short duration. All of that. Where do Postgres uses spin lock? Everywhere. Like anything where multiple processes can sort of update or read from a shared resource. It could be IPC queue. It could be semaphore, it could be, like I said, implementing LW locks themselves. Everywhere, spin locks can be used. Buffer header manipulation, where you're like just setting a flag in a buffer header. It's better to do it with a spin lock instead of trying to acquire a LW lock. The next category is LW locks. These are slightly higher level locks. It provides a lot more flexibility. You can acquire them in read mode and the write mode. Like if there are multiple readers trying to read from a shared structure, they can all hold a LW lock at the same time in shared mode, and the writer would wait, but all readers can basically proceed. There is no deadlock detection for LW locks, so the developers have to make sure that they are acquiring and releasing LW locks in a way so that no deadlocks are possible. And they are released automatically at the end of the transaction. Right, so these are some of the examples, and you would see, like unlike spin locks, LW locks end up showing in user queries or when you are trying to monitor the system. And those who have looked at Postgres systems, they would have seen some of these locks appearing in, say, pgstat activity, where you see that a process is waiting for a certain LW lock to become available. Like wall insert lock is probably everyone would have seen, because multiple processes are trying to log a wall message, and they all sort of, if there is a lot of contention, they might end up waiting for this lock to become available. And proc array, like when you are trying to read for process information, that's why sometimes if you have lots of backends in a system, you might see proc array being sort of shown in system monitoring. You can monitor LW locks this way. I mean, there is, like I said, pgstat activity has a column called wait event type, which is LW lock. And then if the process is waiting for LW lock, you can see in more granularity which kind of LW lock it's waiting on. And Postgres has it sort of, like I have posted a link there where Postgres defines all kinds of LW locks, which are defined by the Postgres core itself. And obviously there could be more if there are extensions which are loaded. Extensions might have their own LW locks as well. Then comes the heavyweight locks. I mean, these are probably the most critical ones from user perspective, because that's where they interact with heavyweight lock all the time. So what are heavyweight locks? They are also called regular locks or lock manager locks, because there is a lock manager subsystem which is like responsible for managing these locks. They typically work at much higher level, like at the table level or views or functions or schema, or there could be other kinds of heavyweight lock as well. They are visible in the PG locks view that Postgres provides. They participate in deadlock detection. So if the multiple processes are trying to acquire the heavyweight locks, and let's say they get into some kind of a deadlock situation where no process can make a progress until some other process, say, releases a lock, but that process is waiting for something else to happen. So if there is a sort of a loop in wait for graph, those are detected by Postgres and resolved automatically, which is different from LW locks, where the developer has to make sure that they are acquiring and releasing locks in a manner so that deadlocks would never occur. All LW locks typically are acquired during a transaction, and they are held till the end of transaction and released when the transaction ends. There are sort of exceptions, which is the advisory locks that we will talk about. And there is a lock queue for fairness, which is again slightly different from LW locks. Now imagine a case where you have many readers, and there is another process which is trying to alter the table, and that process requires exclusive lock or access exclusive lock on the table. Now because there are so many readers, it's entirely possible, and readers don't wait for each other. So the readers would keep acquiring heavyweight locks on the table, and the alter table would just basically remain block forever. The fairness queue kind of solves that problem by making sure that the process which is, or transaction which is requesting access exclusive lock sort of blocks other readers from making progress. Now obviously the feature can also turn into problem, and we can talk about that a bit later. I talked about this. These are a few of the lockable objects, and in PGLocks view you actually see the object type and object ID. So if the transaction has acquired a heavyweight lock on a table, you would see that the object type is relation, and then object ID is probably the OID of the relation. But these are some of some of the major lock types that you would see in a PGLocks. Transaction IDs, for example, if I'm a transaction, I will acquire a lock on my transaction, and others can then, if they want to wait for me to sort of finish, they can wait on my transaction lock, and that's how the transaction waits are implemented in Postgres. The last one, which is the advisory lock, these are special locks, heavyweight locks. These are made available to the application. So application can define their own advisory locks. They all provide the same kind of mechanism that the other system level heavyweight locks provide. But these are, and they don't conflict with any of the other system locks that we just saw. If we drill down to the table level logs, these are typically 8 like some systems like the EPAS, which is the Enterprise DB's advanced server, I think has another log type added to it, but Postgres provides these 8 types of logs on a table. The sort of the most lenient one is the access share log. So every read on a table, it's almost impossible that you try to do something on a table and no lock would be acquired. At least the access share lock would be acquired on a table, even if you are just trying to read a single row from the table. So that's the lenient one. Pretty much, it doesn't block anything except the access exclusive lock. So if you are holding a access share log, another transaction which is trying to say alter a table won't be able to proceed. But everything else like inserts, deletes, all of that can happen in parallel with the reads that are happening. And then there are these different ways. I mean, share update exclusive lock, the row number 4 is little sort of special in Postgres, because commands like vacuum and analyze and create index concurrently, they typically acquire this lock. So a vacuum and this lock sort of conflicts with itself. So you can't have 2 index create index concurrently running parallel in Postgres. Or if you are trying to analyze the table and then trying to build an index concurrently on a table, one process would block on the other process. The strictest one is access exclusive, and typically like vacuum full and many of the alter table commands or cluster command, drop, truncate, all of these take access exclusive lock on the table, which then blocks out pretty much everything on that table. And that's where some of the pain sort of comes in. This is a log compatibility matrix. I don't know, hopefully you can read it. The cross means these 2 logs, they are not compatible with each other. So if you are holding access share log, the only thing that it stops is access exclusive log, which is the the rightmost column. But everything else is permitted. Like 2 processes can hold access exclusive log, access share log at the same time, or even access share and exclusive log at the same time. But access exclusive is most restrictive. Once a backend acquires or a transaction acquires access exclusive lock, almost the table is locked out for everything else. So that was about the table level logs. There is also a special category for row level logs, and these are the 4 types that Postgres provides. So you can, if you run a query, select star from table for key share, it will acquire for key share lock on the rows that are being selected. Or for example, if you intend to update that row after selecting those rows, you can acquire, say, for update lock on a row, and that will block out all other readers, even readers, for those rows. They can read other rows, but they can't read the row that you have locked for update. This is slightly different because Postgres, like I mentioned, it follows MVCC, and typically in MVCC systems, the writers don't block readers and readers don't block writers. But application can make exception and say that, I want to lock out all readers while I am updating this row, and you can do that with for update logs. Now these logs are different because they are not stored in any in-memory structure in Postgres, unlike the other logs like table level logs or function level logs. These logs are stored on disk, and that's why there is no limit to how many row level logs a transaction can acquire. Pretty much you can have a table with billions of rows and you can pretty much lock out the entire table, every row in the table. I won't recommend to do that, but you can do that, and there won't be any problem in Postgres with that. This is also a bit different from other database systems where lock escalation problems become common because they have only a limited amount of space in memory for holding locks, and if you go beyond that, they have to then like look for alternatives or maybe even error out. This is how you explicitly lock a row in Postgres. Like I said, this is slightly different. If you don't, for example, select star from orders where ID equal to 1, if you don't specify for update, it will only acquire access share lock on the table, but there won't be any lock on the row. But if you want to lock out the row, you can do with for update clause, and then there are other additional things that Postgres provides, which could be interesting. Like you want to lock the row, but if it is already locked, then you want to skip it, so that you can have multiple backends working on set of rows, and whatever locks you can acquire, you work on that, and you have like a companion backend which is working on the other set of rows. Let's talk about lock lifecycle. So, typically whenever a transaction makes an access, it could be a read or write access, Postgres will make sure that the table or a row, depending on what you are doing, is locked at that point. And the lock would stay until the transaction ends. There is no way in Postgres by which you can say that I want to forcefully release lock on this table. That's not possible. Postgres basically makes sure that locks are held till the transactions are complete. Locks can be upgraded, like you might start with just a select statement on a table, which will result in access share lock on the table. But later in the transaction, you decide to do, say, insert, update, delete on the table, or even alter the table. That requires a stronger level of locking. Postgres will make sure that the locks are sort of upgraded to the necessary level. But once it's upgraded, it's going to stay there. I mean, it's not as if that statement is complete and you'll again go back to the earlier lock level. That doesn't happen. Locks can be upgraded, but they cannot be downgraded, and they are only released at the end of transaction. So for table level locks and row level locks, transaction commit and rollback sort of defines the boundaries. Advisory logs can be separate, they can be special, and this is where the user has control. User can acquire a advisory log and keep it even across transaction boundaries. But they have to be mindful of what they are doing, because if they forget to release that logs sometime later, but these are advisory logs, so they are not going to conflict with the actual table level logs or row level logs that Postgres is using, but the applications, another transaction might get locked out. Sub-transactions are again something special, because sometimes users think that I started a transaction, then I did something, then I started a sub-transaction, which is typically happens when you do a save point, and then do let's say access another table. In this case, I think I use the same table, but after save point 1, it could be a separate table as well. Now, if you roll back that sub-transaction, Postgres is still not going to release the lock on that table, even if that sub-transaction is aborted. So once a lock is acquired in the main transaction or a sub transaction, it's going to stay till the top level transaction ends, either a commit or abort. Okay, so we mentioned about logs being automatically released at the end of transaction. Prepared transactions are slightly different, and the reason why I thought I would mention prepared transaction is that I have seen cases where customers basically complain about a log being held on a database object. It could be a table or anything, and even if they restart the database, the logs are not being released. And prepared transaction is the only case where that can happen. Like any other kind of log, and if you restart the database, it's gonna go. I mean, it could be even like a row level log or an advisory log. Everything will get cleaned up if you restart database. But prepared transactions, they are resurrected when the database restarts. So those logs can stay across database restarts. And this is an example how you sort of like create a prepared transaction in Postgres. You do begin, you do some write operation, and then you say prepared transaction. Now this transaction is gonna stay active until you either commit or roll back that prepared transaction. So they hold logs. The thing is, they may not even, they show up in PG logs, but typically we are sort of used to figuring out which backend is holding a log, which PID is holding this log. But because prepared transactions are not associated with a backend in Postgres, these logs, even though they would show up in PG logs, the PID column would be, say, 0. So that's a hint that maybe this is the prepared transaction that's holding the lock on that table. So yeah, I mean, there is a PG prepared transaction view that Postgres provides that will show you, what if there are any prepared transactions in the system, and then you can decide to either commit or roll back those prepared transactions. Typically, these things are handled by some sort of TP monitor or a transaction manager that's running outside Postgres, because the very fact that you are using prepared transaction means that Postgres is sort of participating in some distributed transaction that involves other databases or other resources that require atomicity. Lock manager internals. So lock manager is maintained as in-memory data structure. It's a hash table in Postgres. The hash key is typically some kind of lock identifier. It could be DB-OID, relation OID type. This is one example. Depending on what kind of object you are locking, the ID can differ. But that's basically, it's like mostly, I think it's 4 member structure that defines your lock ID. There are wait queues for locks. So like, because to guarantee fairness, Postgres needs to maintain wait queue for every lock. Yeah, so I think we talked about this, and this is where the starvation of lockers can happen. Like a process holds a read lock, then another transaction comes which wants to acquire an access exclusive lock on the table, but because this transaction is holding access share lock, this transaction must wait. Now imagine there is third transaction which is also trying to acquire an access share lock. Now in theory there is nothing which prevents that third process from going ahead and acquiring access share lock and reading whatever it wants to read. But if we do that, then the exclusive locker would starve forever in a very busy system. So Postgres avoids that by maintaining the fair queues. Deadlocks. Yeah, so I think everyone is probably aware of deadlocks, but let's look at why deadlocks happen, right? And a primary reason is because there is a transaction A and transaction B. Transaction A acquires a lock on a resource, transaction B acquires a lock on another resource, and now they try to acquire resources out of order, like on each other's resource, and they both block because until the resource is released, the transaction can't make progress, and resource won't be released until the other transaction makes progress, and it's a classic case of deadlock. Postgres typically detects deadlocks and resolves them by aborting one of the transaction. So you will see this kind of messages all the time in your log if deadlocks are common. Obviously, if you are smart enough and you are avoiding deadlocks, you won't see any of that. So how do you avoid deadlocks? So there are two ways. One is like if you like enforce a consistent locking order in your transaction, deadlocks would never occur, because if whatever is going to wait, only one transaction would wait, but the other transaction will always make progress, ensuring that it does what it needs to does, finishes the work, and then the other transaction can make progress. Or you can acquire all your logs that you want upfront. So if there has to be a problem, it would never happen later. Like you can acquire the logs on these rows in upfront and then update in any order that you want. But if deadlocks happen, or if you see problems in your system, how do you diagnose them? Like this is one way. Like you can look at the PG logs view and see who's waiting for who, or which backend is holding which kind of logs, whether they have been granted the log or they are in a wait state. And if they are in a wait state, why they are waiting? Because someone else is probably holding that log. Now, like I said, if there is a deadlock, things would resolve on its own. But if it's not a deadlock, if it's a live log, for example, a process is just not finishing, and the other process is just is like constantly waiting, you can diagnose those kind of things by looking at PG logs. These are some, I think, these are very popular queries that a lot of users use. Like, how do you find blocking sessions? Don't even ask me what it's doing. But yeah, it will give you, like, given a PID, it will tell you who's blocked. Or you can do a detailed blocking analysis where it will actually show like which process is holding which logs, and then which other processes it's currently blocking. It can be, obviously at a given instant, you can always have processes blocked by each other. As long as they are making progress, I think it's okay. But if your system is sort of stuck and you are seeing some transaction is being, it's waiting for minutes and hours, and you don't expect that to happen, then obviously you can look at the logs and see if it is genuinely waiting for something, and whatever it is waiting for is actually doing something useful. Or, for example, is it a prepared transaction that somebody has forgotten to resolve, and that's why I'm waiting, and that wait would never end until that prepared transaction is actually cleaned up. So all of that information can be sort of obtained via PG logs and PG start activity. Yeah, I think we talked about this briefly. Like PG start activity show you log wait events, and it could be like a log which is the heavyweight log, or it could be a LW log. PG start activity shows you both kinds of wait events, and then more details as part of the, I think, I forgot the column name, but there is another column in PG start activity where it shows you exactly which log it's waiting for. How do you handle these situations? There are two ways. You either cancel a transaction that, obviously if there are prepared transactions, you resolve them. If it's not a prepared transaction, if somebody has opened a transaction in your database and forgot to sort of either commit or roll back, you can decide to cancel that transaction. If that doesn't work, sometimes it happens that a transaction is in a state where it cannot be cancelled. You can then terminate that backend, which is slightly more forceful than the cancel query. Okay, so we have 5 minutes left. Let's talk about access exclusive log and why it is dangerous. And I think I already mentioned this a couple of times, but what happens is if a transaction tries to acquire access exclusive log, it not only blocks itself, but blocks every other reader on that table, because the fairness queue has put the transaction which is trying to acquire access exclusive log ahead of even the readers. And that's why I think it's important to sort of try and see if you can reduce occurrences of access exclusive lock. And obviously, you can't avoid it all the time, otherwise this would not have existed in Postgres. But there are some smart things that you can do to reduce the possibility of acquiring the lock. So what are the operations that actually require access exclusive? This is not obviously exhaustive list, but just an example, like drop table or a truncate can do that. Vacuum full or cluster command acquires access exclusive lock. Luckily, there is repack. Most likely, it's coming in PG19 repack concurrently. This is somewhat similar to PG repack and PG squeeze extensions, but now the facility would be made available in Postgres itself, so that you can actually compact table, sort of get rid of all the bloat in the table without actually blocking the table in access exclusive mode. Instead of reindex, you can use reindex concurrently. Similarly, instead of drop index, you can do drop index concurrently. Even materialized view, you can use concurrently clause. So all of these concurrent, wherever you see concurrently, it typically means that the Postgres is gonna implement that DDL in a way so that access exclusive lock is not needed or taken. I think probably detached partition also supports concurrently clause these days. Yeah, so the bad way to do is you just create index, and even if create index itself only needs to read the rows in the table current state, but because while the index is being built, you don't want new rows to be added to the table which are skipped by create index command. Typically it acquires a lock which prevents all other writes to the table. Reads are still fine, but create index would block all writers to the table. So instead of create index, you can use create index concurrently. You can use reindex concurrently, so that you can reindex all indexes on a given table without acquiring access exclusive lock. Drop also has similar feature, like instead of doing drop index, you can consider using drop index concurrently. Now obviously you might ask why Postgres doesn't do it by default, because these operations are slightly more expensive. Like if you are building a index with concurrently clause, it has to do, I think, 3 passes over the table. So on a large table, it would take longer. There are other requirements as well, which I'm not going into, but for example, create index concurrently needs to wait for all existing transactions to go away at some point. So it can take very long time. Like if you have forgotten to close a transaction somewhere, create index concurrently may not even return. So depending on your use case, you can choose between the two variants. Adding columns safely, Postgres nowadays it supports a default clause. So you can, if you add a new column with a default clause, it's not going to rewrite the entire table immediately. So all the future reads would be supplied the default value from the catalog, and then you can backfill as you need. Similarly, if you want to add a constraint, like if you are adding a foreign key constraint on a table, it will acquire access exclusive lock on the table, which will block it out for all reads and writes. But you can do it by in a two-step process. So you add a foreign constraint as not valid first, which means you are telling Postgres that I don't believe that this constraint will be valid when the command returns. Postgres will only ensure that any future inserts to the table, they guarantee or they honor the constraint. But for any existing data, Postgres is not guaranteeing anything. But that you can do like in a batch process manner. You can sort of validate, and once you are sure that this is okay, then you can validate constraint, which is going to be much quicker, because Postgres is would just make sure that it will still check that the constraint is valid, but it won't log the table. You can do, like if you want to change type of a column, instead of like in place changing the column type, you can add a new column with a new type, and then like sort of copy from old column to new column, and when you are like done, you can just swap the column. So yeah, I mean, these are the best practices. Uh, Keep transactions short and focused, because like we discussed, these locks are held for the transaction duration. If your transactions are small, locks won't be held for long duration. Avoid idle in transaction. This we see like very regularly, even on customer environments. Postgres luckily now supports idle. I think idle in transaction timeout or idle in session timeout. So you can consider using those timeouts to automatically get rid of transactions which someone has forgotten to sort of close. Uh, you should lock resources in a consistent manner that will avoid deadlocks, or you can use facilities like skips locked for queue management. Use concurrently whenever available and when you think is the right thing to do. It might take longer, it might require additional scans on the table, but it won't prevent concurrent readers and writers to the table. Constraints, you can, like, I think at least check constraints and foreign key constraints, they support not valid. I'm not sure if recently more things are added there, but for wherever not valid mechanism is available, you should consider using that. And yeah, set lock timeout before DDL, so that your DDL is not blocked for very long time and then subsequently blocking other readers. Monitor PG, prepare transaction, and then bunch of other system views. You talked about PG logs and PG stat activity, which can give you good insights. There are additional gugs that I haven't mentioned here, like log debug or something like that you can set, or log, is it called min messages or something like that. So after, if a lock is not available after say 1 second, it will start printing information in the log that this process is blocked for so many duration, and then you can go and sort of investigate why it is happening. So I think that's it. Thank you so much.